concepts, and we go through most complex ones through the end. And then I have one Google Colab. I think I've prepared one and shared with you guys before this meeting that we can go through that Google Colab and work on the codes as well. Okay. So the objectives for today's workshop are first, what is machine learning? Comparing supervised versus unsupervised machine learning methods. In supervised machine learning, the differences between regression and classification and types of ML algorithms for each one. And then at the end, we go through some metrics that we use for each one of these models and a few examples. So I usually start my slides with this slide specifically because you can take unlimited number of workshops, but the only way to learn the best is just to do your own project, and doing multiple workshops and not doing any project is not going to help you. So just with this workshop, you can break the vicious cycle and try to do your own project at the same time to learn the most. That's the best way of learning AI. Another thing is that this workshop is mostly introduction to the subject. I mentioned that this is for broader audience, so bear with me with some very basic stuff. And also, we don't. I didn't include any data cleaning methods. So one of the most important steps in data analysis, in computer science, in epidemiology, any data analysis method is data cleaning. You should first know your data. You should know your question and your outcome and how you want to analyze, and then you use your algorithm. And if you have a clean data, a good data, running a machine learning algorithm is going to take you a day or two. But if you don't have a good data, if you don't understand your data, you can just repeat your model over and over and get the same bad result. So, and there is one saying that one of really great professors in AI mentioned, Dr. Marzi Ibrahimi, is that garbage in, garbage out. So if you don't have a good data, your output is not going to be good. So that's something to just consider. So with that, so here is just the basics. So what's the difference between humans and computers? That humans, they learn from experience, whereas computers, they need to learn from data and they need to program and given instructions. Computers can also learn from experience too, but we need to give them data to do so. And that's what we are seeing with our large language models right now with ChatGPT and everything else, that everybody is giving them a lot of data. So now they're becoming more experienced in a lot of things, even more experts than humans. So. And this one, this slide is a cheat sheet of machine learning algorithms. So it's a good start to just look at the types of machine learning algorithms. So usually if you have the way that we categorize the algorithms is that if you have a labeled data, we use the below, like if you have an outcome and it's labeled, you use supervised machine learning. And if it's a continuous variable, you use regression. If it's a categorical variable, you use classification. But if you don't have labeled data, you can either use clustering or you can use dimension reduction methods like PCA or like other methodologies that you can use for dimension reduction. And also there are a lot of clustering techniques that you can use to just classify your, only like cluster your data without any outcome. So here's again same thing. So with supervised versus unsupervised learning, that in supervised learning you have an outcome, and you either classify or do regression. But in unsupervised learning, you create clusters, and you don't have one specific outcome to cluster. One example for unsupervised is, for example, I don't know, you know about how we triage like in emergency departments, like to green, yellow, and orange. This is how we create clusters too. So the cluster of people have something in common inside them. So they have some intrinsic structures that we divide them based on those. In here, with unsupervised learning, as I mentioned, we have some dimensionality reduction tasks. So some examples of this are principal component analysis that I'm going to explain in the next slide. We have some algorithms that we use for anomaly detection, for example, for finding outliers, like local outlier factor, and minimum covariance determinant, or other algorithms. And also with clustering, that's very common right now to use. We use it for grouping similar instances into clusters. So some examples are K-means, hierarchical clustering, and some like Gaussian mixture models too. So now I'm going to explain PCA, or principal component analysis. This is one of the most important methodologies for dimensionality reduction. So I'm going to give some example for this to just understand the meaning of PCA and how we use it. Let's just think of a very simple problem here. So here there are a bunch of friends standing like this, and I want to take a picture of them. And the question is, where do we take the picture from? And what angle would be the best that captures everyone and in their best way? So I tried different methods. First, I tried this angle, then I tried this angle, and then I tried this angle. But you see in here, I can capture most of the faces in this angle. So this is so far the best angle that I can take the picture. This is what really dimensionality reduction is. It means that taking a picture of your data and trying to keep as much as information as possible. And some other examples. For example, in here, I have some dots. So now I want to project these dots on this line. So again, I can use different angles for this. I can do this. You see in here, in the second one, compared to the first one, I'm capturing more data. Like there's more spaced out. They're more spaced out in the second line compared to the first line. So that's actually a better way to reduce I've reduced the dimension, but also I've captured the most important part of my data. So that's again another example. And then the third example is that I have some housing data. So this is actually a real data that I can have. So let's say that with this housing data, I have a bunch of columns that some of them are very similar. So for example, I have number of rooms, I have size, number of bathrooms, schools around, crime rate. So I want to reduce the number of columns here and capture the most important ones. Do you have any suggestions how I can do that? You can type in chat. Add number of bathrooms and rooms, okay? Would that show the whole data? Is there any other way that you would suggest? How can we reduce the dimension of this database? Get rid of size column, okay. Change the rows to columns. So these are all columns, these are not rows. These are 5 columns that I have. Can you group them? Count bathrooms as rooms as well. Okay, that's good. What else? Remove size and group bathrooms and rooms. Okay, nice. Uh-huh. How about the other ones? Okay, these are very good suggestions. But one question, does number of rooms and number of bathrooms, can they also show the size of the house? Size, row, everything else columns. Maybe remove crime rate and schools, and if it doesn't relate specifically to the house. Okay, so one way that we can do it, these are already great suggestions, but one way that we can capture all the data and not remove the important ones is that to categorize them to very, like to lump them together. For example, size of the house, number of the rooms, and number of bathrooms, they can all show the size of the house generally. Because when your house is bigger, your number of rooms are more, usually. Usually your number of bathrooms are greater too. So these are all correlated with each other. And then we can also add schools around and crime rate to location. So these, both of them are some kind of like location information that you can lump them together. So this is a size feature, and these two are location features. So now you see, like with this method, I've decreased the number of columns, but I've kept the important information. I have the one variable that shows the size of the house and one variable that shows the location. You can use zip code, that location of the house. And with these two, I can do my analysis, and that shows all of these 5 columns all together. So that's the way that PCA also works. So this was the example of PCA. Now, how about clustering? So with clustering is another way of unsupervised learning. This is also basically consists of grouping data. So one example that I'm gonna bring up here is customer segmentation. So now I wanna try marketing strategies. So I have this group of people who have tried a specific page in a specific app. And so I have 2 variables in here. I have age in years, and I have engagement with the page in days and week. So based on these 2 information, can you group these customers together? Like, how do you find them? How can you cluster them together with these 2 information? Maybe these 2, they have very similar engagement and they are very similar age. So maybe we can group these 2 together, right? Or these 2, very similar age again, around 20, and engagement is almost the same. So one thing that you can do, because you have two main variable, you can actually create one x-axis and one y-axis, and put all your data in here. And as you see, when I put it like this, now these 2 are grouped together. These 3, the top 3 are grouped together, and then the these 3 on the left are grouped together. So they're very similar. They have very similar characteristic, and that's how clustering works. So usually, so now what I can do for my marketing strategy, I have a group of people who are age 20, who have low engagement, And then I have a group of people who are around age 40 who have medium engagement. And then I have a group of people who are around age 50 that have low engagement. So I can use strategies, marketing strategies for each one of these, like separately based on their characteristics. Any questions up to here? So can we also group them by gender instead and make two strategies, or engagement is more important factor? Usually, like in marketing, engagement is more important. But yeah, it depends on your on your question. For example, in here with marketing, for me, is engagement is more important. So I want to cluster people based on that. And then so create my marketing strategy based on these factors. But sometimes you have other things that are important for you. For example, in medicine, we do the same thing, for example, with ICU patients. We cluster them together based on their like mortality and their need for intubation. So that's my main criteria. So I create my clustering like based on those mainly, and then look at the other factors inside the cluster. Yeah, so it really depends on your question. So that was clustering. Okay, so next we are going to look at supervised learning. So in supervised learning, we have regression versus classification. So let's go through regression. So now in here, we have these three dots, and we want to find the best line that fits through these 3 points. Obviously, the best line is very subjective, and we want to try the line that works well. And since we are teaching the computer to do this, the computer cannot really eyeball the line. So what we want to give the computer is to draw random lines and see how bad the line is, and then based on those errors, make a good line, like the best line that the computer can. So in order to do that, first we try this. We try and we see how bad the line is by calculating the error and the distance of that line from the each point, like this. And then we add these distances together, and that is our error. Then we ask the computer to draw another line like this. Again, we calculate the distance from the points to the line, and then add them together. So here you see we have more error. Then I draw this line. This is much better. So in here again, I add all these distances together, and now this is my error, and it's much better. But the best line right now is this. So I now taught the computer to learn from the error and create this best line in here. So that's what we call this is gradient descent, or with linear regression, we call this least square. So usually, what is gradient descent is that if we think that you're on top of this mountain and you want to find the best way to come down the mountain to reduce the error. So that's called gradient descent. And so that's like how we describe it. But in linear regression, we also call it least squares. And so usually with linear regression, this is the way that we find the best line that fits our fits the these like can cross these lines. So here again, with the gradient descent, think that you want to come from this Mount Everest to down to the bottom of the mountain. And if you go to the left, you have more, your error increases. If you come to the come down, your error decreases. So that's how we call the gradient descent and the error. So you see how I changed the line when I change the line, the error also decreases. And when you come down to the mountain, that's the least error that you can have, and that's actually your best fit line that you can find here, that can cross all the dots. So you can think of linear regression as a painter, and when you look at your data, you can draw usually the best fit line. Now, sometimes your line is not just a straight line. So like here, you can have circles, or even you can, like with the on the bottom, you can see that the curve is actually fits a cubic polynomial. So it's not always a straight line. And that's the good thing about machine learning, that can analyze your data and find the best line for you. That's what the regular statistics cannot do. And that's the favorable thing about machine learning. And with linear regression, we also have other coefficients that we usually report. So we usually report beta. Beta is the estimate of marginal effect of that specific factor in your model. And it shows a unit change in return to the change in outcome. So that's what we usually report in stats. But also we report R squared. This is the estimate of how much beta and alpha together they help to explain the return on a security versus how much random variation it is. So how much your covariates, how much they can explain the variation of your outcome. This is the definition of R squared that we usually report for linear regression. Now, classification. So with classification, now we want to classify your dots. So in here, we wanted to draw a line to separate to the best line that fits your data, but with classification, we want to divide them. So there are different classification algorithms. The first one that I'm going to explain right now is the naive Bayes algorithm. So this is the algorithm that we use for detecting email spams. So now one example for this is that we have about 100 emails, and we have already looked at these 100 emails, and we have flagged about 25 of them like this. These 25 are spam, and 75 are not. So now I want to think of a feature of a spam email, and to find that feature and to analyze the feature, so I can predict what if the future emails are a spam or not. So what do I do? First, I find that the word cheap has been repeated in my spam emails, and so you see in 20 of my spam emails and 5 of my non-spam emails, I have the word cheap that has been repeated. And so here, if an email now contains the word cheap, what is the probability of this email being a spam? You can answer in the chat. Yes, correct. 80%. So 80% is the probability of this this word cheap to be a spam. So now I want to find other words too. So if I have a spelling mistakes, as the chance of the probability of my email to be a spam is 70%. If the email has missing title is 95%. So you see, like when we add them all these together, now with the future emails, I can predict those future emails and if they're a spam or not, by using all these words and the probability of all these words. And that's how this is how the algorithm naive Bayes works. So what are the assumptions for this algorithm? So the assumption in this algorithm is that first, it assumes that there is a presence of a particular feature in a class that is unrelated to presence of another feature. So the assumption is that your predictors, those specific words that we find, they're independent from each other. For example, a fruit can be considered to be apple if it's red or round and about 3 inches, right? But if even if these features depend on each other and upon existence of other features, there is another probability that there's another fruit like orange to be similar like this. So this shouldn't be like your features shouldn't be really correlated with each other. That's why we call it as naive. And so this algorithm is very easy to build and is very useful for very large data sets because it's very simple to work. And but it also is very outperforms highly sophisticated classification methods. And this specific classifier can is as I said, is super fast, and it can make predictions in real time. So that's the one of the pros about this. It can also do multi-class prediction. So and also we use them a lot in text classification, spam filtering, and sentiment analysis. We use this algorithm a lot. And in NLP. So the pros and cons. So as I said, it's easy and fast to use. But when the assumption of independence holds, it performs better than other algorithms, classification algorithms. But what are the cons? So first is zero frequency. Does anyone know what is the zero frequency phenomenon for this algorithm? And have you ever heard of this? Yeah, I think someone said when a feature doesn't occur at all. Exactly. So usually the zero phenomenon is when the probability of that specific feature is zero. So when this happens, the algorithm cannot work. This is known as zero frequency. The way that we do it, we go around this is to use a smoothing techniques. So one of the simplest thing is called Laplace estimation, Laplace. So in this method, we add one numeric number to all the features probabilities. So none of them can be zero. So you add very similar amount to all of them, and then you do your analysis. That's called Laplace estimation. And then it's also this algorithm is a bad estimator. So usually the probability outputs from the predict probability, we don't take it seriously. It's not like this algorithm is not good for calculating that. It's good for finding like a specific keywords. And another limitation of what does assumption independence means? So you see the features that you want to study in your model. For example, you saw that the word cheap or not having title, like these are the features that I'm studying. These shouldn't be correlated to each other. That's the assumption. And it's very hard. Like in real life, it's very hard that your features don't correlate. So that's something that you should be aware of when you use this method. And yeah, so in real life, it's very hard. Most of the features they might correlate with each other, so it's very hard to do this. And next one. So that was naive Bayes. So what is logistic regression? I think most of you must know logistic regression. So in logistic regression, now we have those dots again. Some of them are green, some of them are red. Now we want to try a line that separates these green points from the red points. And again, the computer cannot really eyeball, so we have to draw so many lines and assess the error that the computer makes to predict the best line in the future model. So here, I drew this line. Actually, the computer drew this line, and you see it has classified my dots to red on the bottom and the green on top. You see that the computer has made two errors. There are some greens that are in red area and some red that are in green area. And so now I choose another line, and now the errors reduced. Like I have only one error. The green is now, one green is in the red area. And this is the perfect, like the best line that the computer could generate. And now here the error is 0. So again, the gradient descent here, we use log loss function in here. And that's the way that we measure error in logistic regression. But in real life, it's very hard to like, usually we don't have this like few dots. We might have something like this. Our data might be very complicated, so we cannot really divide these dots with only one line. So what do we do here? So you see now in here, if I draw a circle, I can divide these dots from each other. Or you can draw two lines and separate these dots from each other. So that's how neural network works. Neural network, you have different nodes in neural network that generates these lines. In each node, you generate a different line, and then you combine them together based on the log loss. And at the end, you have your final node where you have two lines that separated these dots from each other. And why do we call it neural network? Because that's how neurons work in our body too. So the first two neurons, they just send the message to the last neuron, and that sends the message to the body. So that's very similar. That's why they call it neural network. We have nodes in our body too, so that's very similar. We can also show this as a ninja. So here in the logistic regression, our ninja can only cut the dots with one step. But then on the right, we need 3 ninjas, each one of them from one dimension to be able to cut this data. So that's how neural network works. Then the next algorithm is support vector machine. So support vector machine is another classification algorithm. In here, you can draw multiple lines like this. So the question now is, which one of these lines, which one is a better line based on what we described from the distance to the line. So what we do the same thing. We draw a distance from each line. And here, we calculate how much that specific line is far from the points, the dots. And we calculate the error. So there is one problem here. You see, if we look at the yellow sign here, the yellow line, it seems that it's very close to failing. It's very close to that red dot. And if you just wiggle it a little bit, you will miss to classify that specific red dot. So, but the purple one, on the other hand, it seems to be nicely spaced from all the dots. And so even if you move it a little bit, it wouldn't miss any of the dots. It wouldn't miss to classify. So now the question is, How do we find the purple line? Well, in the first observation is that we don't really need to worry about these points because they're too far from the boundary. So we forget about them and we only focus on the points that are close. Now, what we are going to use is not gradient descent here. It's called linear optimization. So what linear optimization is that we want to find the line that maximizes the distance from the boundary points, from each of these points. So we want a line that doesn't miss if it moves a little bit. And this method is called a support vector machine. So a support vector, we can also give an example of a support vector as a surgeon. So this surgeon now wants to cut this data and to separate the red dots from green dots. So what she does, she carefully looks at it and just cuts in between. So that's easy. But now, when there is no line here, so it's very hard to now create that cut in here. So we have to do this. So sometimes your 4 points are arranged in a way that in order to split them, you cannot really do one straight line. So you have to have a curve. So what's the other way? Like, is there any other way to cut this data without creating this curve? So we have to think outside of the box. So in order to cut these dots and separate them out, what we can do is to actually create a 3-dimensional space. And so the points are over that plane. And then we have this extra z-axis for the 3rd dimension. So in order to separate these dots, we just separate them with a plane. So it seems like a better solution than the curve, right? So because the plane over here, where it turns out that these two are actually the same methods, it's not different. Don't get confused. It's just when we have dots that are in different dimension, like data has more than one dimension. That's how we use this plane, like 3-dimension, instead of just the line. And this is called the kernel trick in support vector machine. So we can split this data using this plane. And this is actually very similar. So this is called kernel trick. So another same example with the surgeon again. So she wants to cut these apples, but there's no straight line to do it. So what she does, she just move them up in a 3D dimension, and then she makes the cut using a plane. So that's the support vector machine kernel trick. So usually the objective of support vector machine algorithm is to find a hyperplane that is an n-dimensional space. The n is actually the number of features that distinctly classify the data points. And to separate these two classes of data points, we can have, there are so many possible ways, possible hyperplanes that could be chosen. But what we want to have a plane that has maximum margin. That's the very important term in support vector machine. Maximum margin means that when there is maximum distance between the data points of both classes. And that provides some reinforcement because when the future data points can be classified with more confidence. So we are sure that that blue dot on that line is not going to come to the red side. So that's how we define our maximum margin. And here is another way to show it. So if we have dots that are in 2 dimensions, we just drew a line. But if we have on 3 dimensions, it depends on the number of features that we are looking at. We just create these hyperplanes. And so here you see on the left, we have very small margins, but on the right, we have very large margins. And that large margin, these are called the dots that are very close to your margins are called support vectors. So these are the data points that are closer to your hyperplane, and they influence the position and orientation of your hyperplane. And when we maximize the margin of, we use these support vectors to maximize the margin of the classifier. So that's how we built our support vector machine. And so there are some pros and cons for this. So first, this model works really well with a clear margin of separation, and it's very effective in high dimensional spaces. It's very effective in case when the number of dimension is greater than the number of sample. And it also uses a subset of training set in the decision function called support vector. So it's very memory efficient. And usually the cons, what are the cons? It doesn't perform well when we have very large data. And because the required training time is higher. And it doesn't perform very well when the data set has more noise, like the target classes are overlapping. And that's not ideal. And then also support vector doesn't directly provide probability estimates. It's mostly to classify. So for creating that probability estimates, we use fivefold cross-validation. And but that's not very ideal to do that. Yes, the number of dimension equals to the number of features. So when you have more feature, actually it's not the number, it's the type of features that you have. As I mentioned, the same thing in PCA method. It's very similar concept that you can have like a high dimensional data set, or you can have a low dimensional data set. And that's how we lower out the dimension of our data set by using PCA, and then you use this method. So the next classification algorithm is decision tree. So decision tree, I want to give you an example of App Store, Google Play Store. So here, our goal is to recommend apps to users. So each user, based on what they have been using and based on their preference. So we have gathered this table, and we are going to use to make the rules on the table. You see, we have 6 people with different genders and also different ages. The first person is a 15-year-old female, and she downloaded Pokemon Go. And so then the second one is a female, 25, downloaded WhatsApp. If we just first take a look at gender, if we want to split by gender, just say males versus females, we see that there are some females that they either downloaded Pokemon or they downloaded WhatsApp, but males only downloaded Snapchat. So, and some of them also downloaded Pokemon Go. So we cannot really classify this data based on gender. But how about age? If you look at age, so the first one was gender that we saw, like inside each of these categories, we don't have a very specific algorithm that we can find to classify them. So now I'm going to go based on age. So when I divide based on age less than 20 and more than 20, I see all of the people who have less age of less than 20, they downloaded Pokemon Go. But those who are over 20, then there are like more like they're not homogeneous, same as less than 20. So maybe we should divide them now here by female or male. If they're female, they downloaded WhatsApp, and if they're male, they downloaded WeChat. So that's how I divided my I classified my data. So first age less than 20, more than 20, and then I divided by gender. If it's female more than 20, downloaded WhatsApp, and if male more than 20, downloaded Snapchat. So this is the way that a decision tree works. Usually your data is going to be bigger and more complicated than this. This is just a very easy example, but that's how it works, like how it predicts the best way to create the trees that are each of these are called nodes. So we want to create trees that have very homogenized nodes, like inside them they're very like pure. That's the way that we classify the decision trees. Now there's some terminologies that are associated with decision tree. So we have root node, we have internal node, leaf node, parent node, decision node. So what are each? So on top, we have root node. So the root node is the starting node from which the tree starts. And it only has one only child nodes, and then the root node, they don't have any parent node. So the parent node, it actually in any two connected nodes, the one which is higher is a parent node. So usually root node is on top. It won't have any parent node on top of it. And then we have internal nodes. Internal nodes are in between root nodes and leaf nodes. And then leaf nodes are the one at the bottom. And these are end of the tree. They usually don't have any children. And these are called simply leaf of the tree. And so there are some important questions with decision trees. So first, how do we create a tree from tabular data? Which feature should be selected as the root node? And on what basis should a node be split? So these are very important questions. So a regression tree, first of all, we have two types of tree. One of them is regression tree and one is classification tree. It depends on your outcome, on your dependent variable. If your dependent variable is continuous, we have a regression tree. And usually the value is obtained by leaf nodes in the training data is the mean response of observation falling in that region. So the nodes, they divide based on the mean observation. And classification tree is when your dependent variable or outcome variable is categorical. And how do we divide that tree? Is that the value obtained by leaf nodes is in training data is usually the mode response of observation falling in that region. So we usually divide the categorical variables based on the mode of the response. And so to answer all these three questions is that usually the decision of making a strategic splits, it really affects the tree's accuracy. It's very important. Where do we start? From what variable do we start? And how do we split each node? So usually I showed you in that marketing strategy in the app download, you saw that those who were less than 20, they all downloaded Pokemon Go. So you see the purity of that node. So that Pokemon Go was a node. So the purity of that node usually should increase with respect to the target variable with each split. So usually the tree splits when it sees that it creates a pure node. And usually the decision tree splits the nodes on all available variables and then selects the split which results in the most homogeneous subnodes. So it tries different times. So usually when you do decision tree, it's not only one time, it just tries different ways, and then at the end finds the best tree, the best way to have the more pure nodes, and have also based on some other factors that I'm gonna discuss right now. So usually we have different criteria for a decision tree. In order to split, like in order for the algorithm to split, we have different criteria. One of them is Gini index, one of them is chi-square, reduction in variance, information gain. What is a Gini index? Gini impurity, Gini says if we select two items from a population at random, then they must be at the same class. And the probability for that is 1 if the population is pure. So usually it works when with the target, with the categorical variable, the outcome variable should be either success or fail. It performs only on binary splits. And if we have higher value of Gini, means that our node has higher homogeneity. And I don't know if you've heard CART algorithm, CART package. CART is classification and regression tree. That was one of the first ML algorithms. So that actually uses Gini method to create binary splits. And so there is a way that we calculate it. It's not that important. The only important thing to learn is that usually we select the features with the least Gini impurity for the split. So that's the way we split the tree. Then the next criteria that we can create our splits based on that is chi-square. Chi-square, this is an algorithm to find out the statistical significance between difference between the subnodes and parent nodes. Usually what we do, we measure the sum of squares of standardized differences between the observed and expected frequency of outcome variable. And then we calculate the chi-square, and higher the value of chi-square means the higher the statistical significance of difference between subnode and parent node. And that's how we create this split based on this. Then, so usually we select the split where chi-square is maximal. Next is information gain. So usually when we have a less impure node, it requires less information to describe it. And a more impure node requires more information. So that is called information theory. This is a measure to define the degree of disorganization in a system known as entropy. So if the sample is completely homogeneous, like what we saw in that Pokemon node, then the entropy is 0. And if the sample is equally divided, it's 50-50%. And so it has an entropy of 1. So how do we calculate it is just we calculate the entropy of parent node, and then we calculate the entropy of it in each individual node of a split. And then we calculate the weighted average of all subnodes available in the split. And then what we do, we choose the lesser in the entropy, the better it is. So we calculate information gain, and then we choose the node with the highest information gain for splitting. And last one is reduction in variance. So till now we discussed the algorithms for categorical outcome variables, but reduction in variance is the algorithm that we use for continuous outcome variables, like regression problems. And so what do? We usually, the algorithm uses the standard formula of variance to choose the best split. And the split that has lower variance is usually selected as the criteria to split the population. So how do we calculate it? We calculate the variance for each node, and then we calculate the variance for each split as the weighted average of each node variance. And then the node with lower variance is selected as the criteria to split. So these are some criteria that we choose to split our in our decision tree. And these are very important because people are going to ask you, how does your, like when you run your ML model, there are a lot of tree-based ML models, and you are going to get a lot of questions about this. How is your tree works? How did you decide if you are splitting? So it's very important to know these four methods. Okay, so now there is one caveat for decision trees, is that decision trees are really prone to overfitting. Do you know what overfitting is? When the model knows the training set too well. Okay, yes. Yeah, almost. So overfitting is, so usually you remember that let me see if I can bring one example. Actually it's in the next ones. So here is, I think, is a good example. I'm gonna come back again, but just as an example of overfitting. So you see, you remember that I said, so this is our data, and the red one is the line that we are drawing on our data. And so we start from 0 tree and then go to 1 tree, 2 tree, 4. The number on top is the number of trees that my model has created. You see, when we increase the number of trees, now the model is learning how to find like the best line that fits my data, right? But when you come to 128, 256 trees here, so here you see that this is the best tree that you can do. Like this is almost like this tree has fit your data. You have found the best line. But then when you continue, so that's the problem with decision trees, is that it can continue for all and make a tree for all of your rows. So it can continue forever. Like here, we have 1024 trees here. So if you continue after this number of 3, now from this point on, you are overfitting. It means that your algorithm is finding relationships that are not true in real life. It just finds so many different relationship in your features that are not true in real situation, because it's been testing so many times, like testing everything with each other, and that's wrong. So that's called overfitting. So, and that's one of the disadvantages of decision trees, is that they can overfit very easily. And there are some ways that we can avoid overfitting. One of them is that we set constraints on tree size. So there is a way that you can, usually when you run your model, it doesn't matter what type of model, like from all the models that I mentioned, in all of them, first you start with no criteria. You just create one very simple model in the beginning to just see how your model works without any any criteria. And then what you do, you usually do grid search. So grid search, I'm going to explain it in the next slides, but grid search in general is when you try different regularization parameters in order to avoid overfitting and find the best model. And you usually use tenfold cross-validation for that. So what it does, for example, you give your algorithm to test about, I don't know, like I have like 20 parameters that I'm gonna test. It will test that 20 parameters 10 times. And then out of those 10 times, it gives me the best model that has the best accuracy, least error, but also it avoids overfitting. So because it knows when to stop your model, like from where to stop it. So that's how the setting of constraint on tree size works. So this is with grid search. And then tree pruning. There are some packages that help you to prune your tree. Um, Pruning your tree is actually a literal word. It's like this. So you see these orange ones in here. So when you use pruning, it just removes these leaves that are causing overfitting in your model. So that's how it works. And so these are the two ways that you can avoid overfitting. I will explain the grid search more in the next slides. There are some advantages of decision trees. So first, it's very easy to visualize and interpret. So the same example that we had with the app, like it's very easy to understand how the algorithm works. It's very useful in data exploration. It doesn't require data cleaning. You can just try it out to see like how your model works. And the data type is not a constraint. It works on categorical and numerical data. But what is the disadvantage? First is overfitting that I mentioned, and second is it does not exact fit for continuous data. So why? It works on continuous data, but why is it not a good fit? It's because what it does with continuous data, do you remember age here? Um, Here, you see with age, it was a numerical data in here, right? But then my algorithm created a category of my age based on the mean. So this is not a good thing in stats. When you make a category of your numerical variable, of your continuous variable, you lose information in here. So that's one of the limitation of decision tree. Okay, so now, I think I just explained gradient descent, but just to go over that one more time. So gradient descent is that when you, for example, suppose you are on top of this mountain, you want to come down to the lake below the lowest point of the mountain. So the direction that you move, where you have the lowest cost, the lowest error, is the best path, right? So that's what is called gradient descent. You can also see it on top on that graph. You see there is this graph on and in the lowest amount of that graph is where you have your gradient descent, and that's where you have the lowest error. So that's what we call in machine learning. It means that we have least error. So there is also another concept in machine learning that is called learning rate. So the same graph, so this is the graph that shows loss function. We said that here on the bottom, we have minimum, on the yellow point, we have minimum loss or minimum gradient descent, minimum error. But how our model works here is important. So learning rate means the size of the steps that you take to come down from that mountain. If you take bigger steps, you can be really fast. Like you can run the mountain, right? You can run and reach the bottom of the mountain like in 1 hour, or you can take a very small steps and reach to the bottom of the mountain in 10 hours. So it really depends. But both of them, they have limitations. So if you have big steps, so your learning rate is big here, there is a risk that you might miss information, miss some relationships. But if your model goes in a very slow and the steps are too small, your learning rate is very small. So it's first of all, it's very time consuming, and it can be very precise. but your algorithm is taking too many iterations. So again, there is a risk of overfitting here too, and takes a lot of time. So we have to find the middle ground, and that's this is another thing that we usually find out using grid search. Okay, so I'm just gonna go through your questions. The last one, can we say because it deals with discrete values, having continuous data makes the tree too big? So actually this is how the tree works, right? The tree works based on the mean. It divides it just creates that a split based on the mean of observance. And so this is what is the limitation. Usually with other algorithms, it just use the numerical variable as is, and then you can create this PDP plot to see what is the relationship between that specific numerical variable with your outcome, so you don't lose information. But usually when you create a categorical variable from your continuous variable, you lose information. Because now I categorize based on less than 20, more than 20. But what if is like the relationship between age and my outcome is not linear, and then I have a peak point of my outcome in after 80. So I want to see it. If you create categories, you may lose this information. So that's why they usually suggest to keep the continuous variable as is and don't make it categories unless like the relationship is very weak, or you know that your continuous variable has a linear relationship with the outcome, then you can maybe make a category. Yes, I'm gonna explain the grid search again in another slide with more examples. And I think that's it, right? Any more questions? Yeah, I think that's it. So next one. So right now we just learned about some basic like the single predictive models. So these are like linear regression, single decision trees, support vector machines. These are all work on a single predictive model. But there are other models that called bagging and boosting method. So these models they work by combining multiple models together to create an overall ensemble. So in bagging method, you see that the models work in parallel, but in boosting method, that's my favorite one, the models work by learning from each other. So here we create one model, then this model has like a specific error, and then the next model learns from the error of that model, and then the next model learns from the error of the previous model, and finally the final model has the best is the best model with the lowest error. So that's how boosting works. So usually bagging and random forest, they as I said, they work on combining multiple models together, and usually the new predictions are made by combining the predictions from the individual base models and to make that ensemble. So they average in the regression. And since averaging reduces the variance, so bagging, and so one example of bagging in random forest, usually applied to models that have low bias and high variance. And but boosting is a general algorithm usually for building ensembles out of simpler models. So we call them shallow trees. And usually we apply boosting to models that have high bias but low variance. And I think, yeah, that's it. Okay, so this is one, I think, good visualization of how boosting works. So in boosting, you see there is a sequential ensemble approach. So you first train your model, create a shallow tree, and then this tree has some errors, and then you train another model based on that, and then test it on another part of the data, and find more errors, and then train based on that. So this continues until you find the best model. So usually you start with a weak model and then sequentially boost the performance by continuing to build new trees and to finally reach the best model. And I just showed you this. So this is one example of how like this boosting works. It starts from a very shallow trees, but at the end, you see, if you don't be careful, like in here, you are starting to overfit. So you should be very careful of how to avoid this overfitting in here. Okay, so there are some of the limitation of bagging, and some of the good things about bagging is that first, bagging can handle overfitting, reduces the variance, independent classifiers, but boosting, it can overfit, it reduces the bias and also reduces the variance, and it's a sequential classifier. Okay, so now we are going through some boosting algorithms. There are some famous boosting algorithms. So the first one is this gradient boosting machine was the original package that was used for boosting, but now everybody is using XGBoost, the extreme gradient boosting machine. So XGBoost, it has some like advantages compared to GBM, is that it has certain features. For example, one of the most important points is that XGBoost, it implements parallel pre-processing, and that makes it faster than GBM. Also, it has variety of regularization techniques. I mentioned that for reducing overfitting, we use these regularization parameters using grid search. So XGBoost has a lot of these, so you can work on those techniques to be able to avoid overfitting. And also with XGBoost, it can handle the missing values. It's very important. Usually decision trees, they cannot handle missing value. You have to impute before running the model, but XGBoost can handle the missing values. So that's the good thing about it. Then the other type of GBM is light GBM. Light GBM is another boosting algorithm, again based on GBM method, but the only advantage is that it can work on a very, very large data set. So you can work like in genetic data, you can use this light GBM. And usually uses histogram-based method for selecting the best split. And yeah, so generally is almost the same. It's faster and has lower memory usage. That's why it's good for genetic data. The next one is cat boost. So cat boost is a boosting algorithm that can handle categorical variables. And so that's the only advantage that it has. Here, these are the steps of running a machine learning algorithm. So we went through all these different models: logistic regression, support vector machine, random forest, boosting algorithms. So all of these algorithms, they have their own hyperparameters and regularization techniques to be able to first get the best model with the highest accuracy, lowest error, and also to reduce overfitting risk. So these are, I think this is a really good graph that shows the steps of running machine learning algorithms. So the first step is loading and pre-processing data set of interest. So as I mentioned in the first slide, so the first most important, like 80% of your work in a project is to create your database, to make your database clean, and to make sure you understand your data, to pre-process it. That's the 80% of your time, and then the next 20% is running these algorithms. If you have a good database, running the model is super easy. And then you select your ML models based on your outcome, based on your features and data sets. Some of these, they can work on large data sets, some of them are not. Some of them perform really well with like many features, some of them not. So you can just select based on the different, like your project essentially. And number three, the step 3, here you have to do hyperparameter optimization using cross-validation. That's the grid search that I'm gonna go over that like in the next slides. And then step 4, we train. So at first I told you, you have to train a very basic model in the beginning, and then you do this hyperparameter tuning, and then you train your final model based on these parameters, and you have your final results. But then you always test on your test data. So you usually when you want to run machine learning algorithms, you train your model in your trained data set, and you usually have a test set, a separate test set that is completely separate from your training. You can never combine your test and train. Your test should be separate and just put aside. And when you train your final model, you are sure that this is the best model that you have, then you test it on your test data. And this is where you assess all those model metrics, the model accuracy, errors, like everything else is just on the test set. And that's one of the ways to avoid overfitting too, like to make sure, because when you try your model in a test set that your model hasn't like seen it means that like you are actually trying it like in a separate data set. So your model can, if you see the same relationships that you're seeing in your train set, it means that your model is good. But if you are not seeing the same model metrics in your test set, it means that you have overfitted in your train set. So you have to rerun your models. And one of the best test sets is that, so usually you can divide your database to, for example, 70% train, 30% test. But this is called like, this is usually like within one database. But the best way to test your algorithm is to also try it in an external database to make sure that your model performs well in that external database too. So that's another way. So this slide shows some XGBoost parameters. So usually, because I'm gonna the codes that I have for today are for XGBoost. This is one of the best algorithms for running tabular data. So there are general parameters that guide with overall functioning. There are booster parameters, and then there are learning task parameters. So general parameters is the booster type. So if it's the outcome is linear, we call it GB linear. If your outcome is a categorical variable, we call it GB3. And it depends what kind of model are you using. Are you using a tree-based model or are you using a linear model? Sorry. And silent means like if you want to show like the messages or not, if you want to print the messages while running or not. And end thread is actually this is used for parallel processing and number of cores in your system that should be entered in the when running. So if you want to run on all your cores of your computer, so you can select here. Then we have booster parameters. So I have highlighted the important ones with red here. Eta. Eta is very similar to learning rate. Do you remember that I mentioned learning rate is the speed that your model can, the iteration of your model? It should, when it's very high amount, it means that it's going very fast. So it might lose some information. But if you decrease it, it just takes very small steps. It takes more time. So usually what we do, we start from like a larger learning rate, and then at the end we decrease it, because first we want to see how our model runs like in a short period of time. Then we tune our parameters and decrease the learning rate. The next one is maximum depth. So maximum depth is actually the maximum depth of the tree. And so this is very important too. Usually we set this in the grid search with different parameters to make sure that we are not overfitting. This is one of the parameters that we use. Subsample. Um, Subsample is same as so usually the fraction of observations that are randomly samples for each tree. So that's subsample. And then whole sample is the columns that are randomly fraction of columns that are randomly sampled for each tree. And then 10 is lambda. So lambda is one of the regularization terms for XGBoost, and usually we use it to reduce overfitting. Like we can also do it like at the end. If you don't include it in the grid search, you can just include it at the end. And alpha as well. So alpha is another regularization term and that we use. Then there are some learning tasks. So oh, this slide is actually very important. This shows the evaluation metrics that we use. So first objective, you see on top I've written default reg linear. So this means that that's for linear regression. We have binary for logistic regression, and we have some multi for multi-class classification as well. But you can choose based on your outcome here. And then we have evaluation metrics. So number 1 and 2, these are for your regression. For linear regressions, we use these metrics: root mean square error and mean absolute error. And number 3, 4, 5, 6, and 7, these are for classification that we use. Like AUC is a very common one that we use, or log loss. It depends. And seed is actually a random number that we use for generating reproducible results. Okay. So general approach, as I mentioned, we usually choose a relatively high learning rate, and then we tune 3 specific parameters that I mentioned. We tune the regularization parameters that are lambda and alpha, and then at the end we lower our learning rate. This is one example of overfitting that I wanted to show. So here, the default model is so you see the train is red and test is with blue in the graph. And in the left, we have XGBoost classification error, and on the right, we have XGBoost AUC. So that's the different model metrics that you can use. So our model is performing fine, but until 300 estimator. So you see after that a specific tree number, the error the train and test set are actually, the error is they're not together, like the graph are splitting. So that's how you know that your model is now overfitting, because the error in train and test are different now. So usually what we do in here, when we see something like this, we use early stopping grounds. So this is a parameter to stop execution when we see there is no improvement after that specific tree number or estimator. For example, if we run that early stopping grounds, what it does, it creates a table for us, and it will just gives us the number of these estimators, and then it will give us AUC. You see, like from 200 or 300, the AUC remains the same, but the error increases. So that's where you should stop, and you cannot like continue your model to avoid overfitting. So that's the way. And finally, grid search. So grid search, here you see that for hyperparameter tuning, this is for XGBoost, but it's very similar in other algorithms too. Other algorithms, they have different parameters, but generally the tree-based ones, they're very similar. So here you see that I have my learning rate. So I have put 0.1, 0.01, but usually I do even more. Like I do 0.03, 0.05. Like you can add too many numbers. But the problem is if you add more, then like even with this amount of grid search, it will run about 2,187 models only with these parameters. And just imagine how much time it takes just to run all these models. It might take hours. So first, just run with very few number of like parameters. And then if you see that your model is not improving, then add more parameters and run the grid search again. That's the way we usually do. And another way to reduce the amount of time is use GPU, or for grid search to use randomized search CV. So that's one package that we use in Python. What it does, it doesn't test all of these parameters together. It just randomly selects them. It's less accurate compared to if you like select all of these, but that's the way to save time. So it would reduce the number, like the hours that you need to train your grid search. I remember once I was in my first project, I was like, it took me 1 day or half something to just run one grid search, and that's just crazy. Okay, so these are the parameters that you can choose, and yeah, you can search from different papers, published papers, to see, like people usually report what parameters they have used. You can generally find it, and try with small numbers, and then increase the parameters. And are we out of time?
No, go ahead. We have still time until 2 hours. Yeah.
Oh, perfect. Okay. So, I think I'm almost done with my slides. We can hopefully, yeah, I think I can finish by 30 minutes. So the next thing that is very important in machine learning is how to interpret your results. So up until now, we just studied the types of machine learnings, and like how to run the models, how to do grid search, to tune the model. But at the end, you have your model, how to interpret it. That's the important thing. And usually in medicine, they're not really pro machine learning or AI is because of this problem. It's just that machine learning algorithms, the most of them, they're like black boxes. You can just report the model accuracy, the error, but what goes into it is very hard to explain. There are some packages that help us to explain the models, but it still is not that perfect. Like it's not odds ratio for logistic regression, or beta for linear regression to easily understand like the model. In machine learning is kind of hard to explain how the features are created, like how the top features are selected, how like they're correlated with each other, what's the effect size. Like it's very hard to explain these. So there are some packages right now that help us to interpret the outcome a little bit. So first is feature importance. So what we can do with feature importance is that you can select the top features in your model based on all those. Do you remember the 4 criteria that I said? Gini index, chi-square variance, information gain. Based on all these information and then a number of times that a specific feature appeared in your tree, you can select your features and have an order of them like based on those information. So that's very useful actually because with machine learning you can assess the interaction of different features together, and then you can just have an order of the most important features to the least important features. And then what we usually do, we take those very important features and run like logistic regression and create like odds ratio or beta just to explain like the relationship with the outcome. But you can just report the important ones too. This is a great way to do feature selection. So that's one. The second way is to create partial dependence plots. So partial dependence plot, I think I have it in my next slide that I'm gonna show it to you. It actually shows the direction of change of your feature with the outcome by considering all the other features. And that's a really great way to show how your feature changes with the outcome. It's a really great way to explain your results. And there are different packages. The most famous one, I think you might have heard, is Shapley value or Shap value. And this is a package that creates all these feature importance partial dependence plots, but it has its own criteria of like reporting and like a scoring. So that's something new that is now is very common to use for XGBoost, especially for XGBoost models. So with feature importance, as I said, so based on feature weight, mean gain, and also sample coverage, we can select the most important features in our model and create like a figure like this. So feature weight, it shows that the score is calculated based on the number of times the feature appears in the tree. With gain, the score is calculated based on the average gain of the split, which uses the feature. And then with sample coverage, the score is calculated based on the average coverage, number of sample affected by the split. So these are different ways, and you see different variables are on top based on these different methods. And also, another way to assess feature importance is just to, because I mentioned that XGBoost and boosting models, they're tree-based. So you can actually create a decision tree like this for your results. So this is also very easy to understand because you can see like the top features and how they divide into like other features. Then partial dependence plot, that's my favorite, is so this is the to understand the marginal effect of each feature on the predicted outcome by considering other features. So this is very valuable. And so this is based on the mean effect, but this one is ICE, individual conditional expectation ICE curve, is very similar to PDP. So that red plot is actually PDP, but you see each one of these black lines, they're each individual. So you see how they're concentrated like very close to the mean of that effect. So here you can see if the effect, for example, on the graph on the right is centered, but on the left is non-centered. So you can see if the effect has like a greater confidence interval or lower confidence interval, and how like each individual is associated with the outcome. That's very nice graph. Yeah, I think that's it for model explainability. Any questions still here? Okay. Okay, so the last slide is about so different metrics. I'm just gonna go over this very quickly so I can show you the Google Colab. So the first rule is that, as I told you, you should never use your testing for training. You should never combine your test and train. So make sure that your test set is separate from the beginning and you don't mix it like somehow when you build your model. So you can test your model and your test set. So that's very important rule. Then now we are going to go over some model metrics for classification. So for classification, what we usually create is this table. And we call it confusion metrics. Here we have uh, like if the patient was really sick and was diagnosed sick, so that's a true positive. I think all of you might know this. If the patient was sick and diagnosed healthy, is false negative. If the patient was healthy but diagnostic, that's false positive. And if the patient was healthy but diagnosed healthy, that's true negative. So this is the table that we use, confusion metrics that we use for assessing model metrics for classification. And if our model classified our outcome correctly based on this. So first of all, is accuracy, model accuracy. So in model accuracy, we want to see out of all the patients, how many of them were classified correctly. So how do we calculate it? We have the number of patients who were diagnosed sick and correctly, and the ones that were diagnosed healthy correctly, and to the total number of the patients. So the overall model accuracy is 90%. But then model accuracy really doesn't show if our model could predict the healthy people better or sick people better, like if it has better sensitivity or a specificity. What do we do here? In order to assess that, we use different metrics. So first is precision. So with precision, we want to see out of the patients that were diagnosed with an illness, how many of them were diagnosed correctly. So we want to find the true positive ones. So what we do, we have that those number of patients with true positive and to all these patients who were diagnosed sick. So that's the precision. So we have two examples here. One of the examples is for diagnosing the patients. So here my precision for diagnosing the patients was 55%. But the precision for assessing the spam folder, spam emails in my overall email was 76%. So 76% of the time, my model could identify the spams correctly. Then there's another metric called recall. Recall means out of sick patients, how many of them were correctly diagnosed as sick? So in here, we want to first find those who are diagnostic and were actually sick to a total number of those who were actually sick. So 83% is the recall of my test. And for my spam folder, out of the spam emails, how many were correctly sent to the spam folder? That was 37%. That's low. So you see here in my test, in my medical test, the precision was 55%, but the recall is 83%. But in a spam detector, the precision is 76% and the recall is 37%. So which one is better? Actually, it really depends on your outcome and what do you want from your outcome. With my medical model, I want to have high recall. So I want to diagnose the sick patients. That's what's very important for me. But with my spam model, I want to have high precision. So different outcomes might in different tests, you might have like different priorities. So that's what you choose, like the model, the best model based on these. What is F1 score? So when you have the average of this precision and recall is F1 score. So it just the average. So it's not that much informative compared to precision and recall. Squared error, MSE, mean absolute error, R squared, or coefficient of determination, and root mean squared error. The most common one is MSE and also R squared that we usually use. But yeah, it really depends on your outcome, and you can use multiple metrics when report your outcome. Okay, so now we go over some examples. So for this Google Colab that I think you have it in hand right now, I've used income data. I also gave you a link to be able to download this database. This is a 1994 census income data set. It's publicly available. It has variables such as age, years of education, marital status, race, and usually what I'm gonna do in the Google Colab is to predict the income from all these features. So I'm just gonna stop the screen. Okay. So this is the Google Colab. So you can download this data set from here, or I think other data like other websites as well, because this is a free data set. And you just load the data set in Google Colab. So one thing that I wanted to mention, so you can see like different features in my model, in my data set, and you can see the descriptive, mean, standard deviation, and that's very important to check before analyzing, like to clean the data, make sure that the data like makes sense before analyzing. For example, I did some descriptive analysis. I created a histogram for my continuous variables. And also, so here I can have better visualization of how my data looks like, and what's the minimum, what's the maximum. Then I also have created some plots for my categorical variable. So here, I think this is a very good informative plot, because now I can see that private sector, this is work class, and the private has the majority of my working class compared to state government, federal government, self-employed, self-employed income, again, self-employed, no income, self-employed income, and local government. So we have a lot of other categories, but this one has the majority. Usually when we harmonize the data, it really depends on your project. If you want to see all these factors or not, you just want to compare private versus governmental. You can create, you can harmonize your categorical variable, especially when you see one of them is really skewed like this, and add these together to create two categories compared to creating, like having this multiple categories. So depending on your project and your data set, you can harmonize your data. It's very important to do it with someone that is like professional in your field, because sometimes when you harmonize different levels of a categorical variable, sometimes it doesn't make sense. You might make a mistake. So it's very important to make sure that you're combining values that are compatible with each other, not like everything together. That's very important to note. For example, with education, if this was like a project that I was doing, I would combine this education based on US-based or European-based education system. There are usually 4 or 5 categories for this education, like postgrad, undergrad, based on different definitions and based on how the data was retrieved. Like, is it a database that was from US? You use US definitions. If it was from Europe, you use that. Like, they have different educational systems. So we can harmonize this for sure. We need to harmonize. Then marital status, same thing. Like usually we do we add like divorce separated together, like married together. So you can like harmonize again, based on like if they're very similar, you can harmonize them. And also you can take a look at other publications. One thing that I just did for this study here was to this one. Like, this is crazy. This is the plot of native country. It has United States, that's the majority, but then the rest of the countries, they're almost zero. So for this, what I did, that's the only thing that I did harmonization for your project, is to create a US versus non-US. So that was the only, but again, like with your data set, you can decide if you need to harmonize or not. So I did this harmonization, created two levels for this variable. So that's the first step, data cleaning, understanding your data. Then next step is pre-processing. So I explained harmonization. Now you need to do for your numerical variables, you need to scale them, because as you saw here, your numerical variables, they have different units. So for example, here we have hours of work. That's the number of hours. Here we have capital loss. Here we have capital gain. Education number of years of education. And then we have age. So we have different variables with different units, and it's very hard to compare these, especially when you want to analyze them together in a model. So what we do, we usually scale the numerical variables, and with the scaling, there is like a scaler that you can use in Python. That what it does, it creates a z-score from your variable, all of your variable, and based on the standard deviation and the mean of that specific variable. So that's very helpful to do. Then for your categorical variable, what we do, we create dummy variables. So usually with categorical variables, if there are two levels, like yes and no, if they're native US, yes, no. If sex is female, male, that's easy. Machine learning algorithms, they can handle this. But when your categories are more than two levels, for example, if the color of the eyes is green, blue, or like brown or black, like 4 levels, or I don't know, like education, or like there are a lot of categorical variables that especially they are not ordinal, and they're just like different categories, and you cannot really combine them. So for that, you need to create dummy variable. What it does, it just separates out each of these categories and then creates a yes and no column based on that specific category. For example, with here with marital status, what it does, here, for example, so one category would be not in family, yes and no, unmarried, yes and no, own child, yes and no. So you will have different multiple categories. And I've just put the reasons that this is very helpful in machine learning, because so usually especially if you have numerical, usually machine learning algorithms, it will require numerical input. So each category, it has a numerical index. It has 1, 2, 3, like red is 1, blue is 2, green is 3, and it will count it as ordinal unless you create this dummy variable. And then usually with binary features, it's very easy. It will make it as 0 or 1. So for example, with sex, it will be men, yes and no, or female, yes and no. So that would be easier to understand also. And when you create your feature importance, it's also easier to understand your outcome, because when you have multi-level like features, it's very hard to interpret in machine learning. So that's why we create this dummy variable. So for that, I created these pipelines. So what my pipeline does, first, I will divide my categorical columns with my numerical columns. And then I create, so I mentioned that XGBoost can handle missing data, but I always impute my data. There are a number of ways to impute your data. I think that itself requires another session, how to do imputation. You can either impute your missing data based on the median or mean of your variables, or mode of your variables, or with categorical ones if they have with the most frequent ones. And one of the best ways to do imputation is to do multiple imputation. So with multiple imputation, it will predict the missing data based on the whole data set. So that's the most powerful, like the most common way of imputation is that. But for now, I just chose a very simple imputation method, is that it just replaces the missingness with median, and for the categorical one, it chooses based on most frequent. Then I have a numerical pipeline. So with my numerical pipeline, what I'm going to do first, I'm going to impute, and then I'm going to scale and create a z-score. And for my categorical variable, again, I'm going to impute, and then I'm going to create a dummy variable that is called one-hot encoding. That's the method that we usually use. And what it does, it drops the first variable. For example, the first variable for each of these levels, it will be dropped and compares the other levels to that specific variable. That's the way it works. Then after I process these, then I combine them together, and then I have my final data set. So in my final data set, my categorical variables are all as dummy variables, and my numerical variables are in z-score format. And how do we know it's z-score? Is based on this. You see, like, we have negative values with the z-score. And it's good also to look at your data after this process to make sure that you did it correctly. Because here it removes, with this pipeline, it removes the top row, the name of the column. So you should make sure that you just put them back, and if your data set is in a data frame format. So that's always good to double check. Now I have 59 columns compared to the beginning. And I can see, like, different variables that are created based on, like, for the dummy variables. I can just double check. So that was the pre-processing. So now next step is to create so first you want to create a data set, sub-data set of your features. So you will remove your outcome variable in here, and my outcome variable is income, and create a data set that has only your feature names. And then another data set has this has only your outcome variable. And also usually you have ID. Make sure you drop your ID in your features too, because then it will count your ID as one of your variables. Just make sure it's correct. You can also double check this too to make sure what it is inside them. And then step 3. Now you start. So that's the final happy place, is just train the model. It's the easiest part. So first you split your data so your features to test and train, and your outcome to test and train. My test size is 20% of my variables. And then step 2 in here is to train the base model. As I mentioned, in the beginning, you don't want to add any parameters. So here I've used, because my outcome is categorical variable, I've used XGBoost classifier. You can import XGBoost classifier from XGBoost in Python. And then, so I just run my base model here. and evaluate the metrics that I mentioned before, AUC and error, to just see like to have a good sense of how's like my base model is working. And then I also can calculate it like the CPU time here to see how much it took just to run the base model. And now I'm assessing my base model. So for assessing my base model, I want to have accuracy, and I would like to have all those metrics that I mentioned: precision, recall, F1 score. And you see my precision and recall is quite good. Like it's 90% precision and 76% here. So it's really good. The accuracy is also very good. This is, of course, is an example. In real life, it's not going to be like this. Then I also graphed it here. So here you can see that error. Do you remember I said the moment that these train and test start to like split from each other, that's where you're overfitting. So this is very helpful. Next step, I'm going to do hyperparameter tuning using grid search and cross-validation. In here, I used some of the important parameters like learning rate, column sample, subsample, maximum depth, and number of estimators, lambda, that was for regularization. And also for the scoring for evaluating my model, I'm going to use AUC. And here is very important. I'm using 10-fold cross-validation. You can start with 5-fold to have a sense of how much time it takes, and then increase it to 10-fold. Then you can finally from here, it might take like so for me it wasn't that bad because my data set was very small. So it took like 5 minutes only. And so because I also used randomized CV search, you remember I said that you can use randomized, so it would randomly choose all these parameters and test on your model. So that fasten things. And then finally, I have my best model from those best parameters. So this is the best score, and these are the best parameters for my best model. So these are the hyperparameters that I found out from my cross-validation. Then I will assess my model now using these methods. So here you see my model accuracy is now 88%, and my model precision, recall, they all increased a bit. So this is the way, and usually so usually your test and train should be very similar to each other. If you see there is like a lot, now here is really good. And just so the n estimator here is 300, and I just want to go up, so it's around here. But I guess you can also like cut it more. Maybe this is also overfitting, but a general rule is that your train and test model accuracy shouldn't be like so much different. Like they should be also the precision, recall, or the AUC. They should be very similar. If they are very different from each other, it means that you're overfitting. Next step is the feature importance, and so I've done based on those 3 criteria that I explained before: feature weight, mean gain, and sample coverage. And also I created one decision tree here, so it's easier to understand like how those splits work. Finally, it's the SHAP value. So this is a very famous way to for model interpretability. So you can report SHAP value and create this SHAP plot. I love this plot. So here on top, these are based on the most important features down to less important features. And so when it's red, it means that it increases the outcome. When it's blue, means it decreases. So it has negative effect on the outcome. And so you can see like here, the reason is really nice is that it shows the distribution of your result. It's not only like that a specific direction. So some of the patients, they decrease, some of the patients, they increase, but generally, like for example, this increases the outcome, like the capital gain. So you can have a good sense of what is the direction here too. And I think there's one missing. I guess I had PDP plot here. I'm gonna add PDP plot here too. But with PDP plot, you can also see the direction of each one of these with the outcome. Yeah, so you can try this. Try to run it like yourself, and for sure you're gonna have a lot of errors. Like but that's how you learn with the errors. And yeah, see how it works. Like play around, especially like in the beginning, with like different variables. Just remove different variables and then see how it like your model changes, and then you can play around with your like grid search and see how your like if your model improves or not. So that's the best way to learn. And then you can of course start your own project. But usually, so this was only XGBoost. Usually we don't run only one model. What we usually do is we run different models, specifically like different models from different algorithms. For example, one bagging, one boosting, one tree-based, one neural network, and then we compare them together and we choose the best model from that. So that's how we usually do. It's not just running one machine learning model. It just we try to compare different models together and choose the best one for your outcome. Yeah, that's it. Let me know if you have any question.
All right, thank you so much, Dr. Azizi, for the wonderful presentation. It was really informative. I appreciate that. And okay, as we are running out of time, I'm gonna just wrap it up quickly. Just a quick reminder that our tutorial TA sessions will be happen on Tuesdays, every Tuesday at 5 p.m. But we will send you a reminder email in advance. And yeah, I guess that's all for today's session. Thank you everyone for your time, and I hope you all have a great night. See you on Sunday.
Of course, thank you all.
Thank you.